Okay, let's get started. So the theme of the week is skeletons. We ended last lecture about 3/4 through the material, so we're going to awkwardly finish that one off and then start on the next subject within the topic of skeletons. Before I forget, my office hour is on Wednesdays, and I hold it outdoors, outside there. I know I've said this before, but in case you missed it. And so on the weeks that I'm not lecturing, I'll just sort of show up outside there for anybody who wants my office hour. And then if nobody wants it, then I'll just walk home from there. Sadly, just walk home. So anyway, I'll be there after class. Okay, so we were talking about this displacement advantage, mechanical advantage. If mechanical advantage is high with a lever system, then you're going to get more force output per amount of input of force. Okay, so you can think of it as the amplification of force, and that is perfectly the inverse of the displacement advantage. There is an assumption implicit with that relationship, but we'll just leave it as this geometric principle that they're the inverse of one another. So if you have a crowbar or a single joint in a skeleton that is organized to generate a lot of force, then it's going to generate relatively little displacement. So if you were to increase, for example, this part of this crowbar, make it longer, then you can, for a given amount of input force, generate a lot of output force, but you have to pull it a greater distance in order to get it to go the same distance that you would otherwise get with a smaller lever. So they're inverse relationships. And so we concluded that, first of all, the displacement advantage amplifies the short displacement of muscles, and that a high mechanical advantage does this thing of enhancing the force output, and they're the inverse of one another. Okay, so what I want to do now is take these ideas and apply them to real biological systems. This is the more interesting part of the lecture. I had mentioned, or I had shown you how locusts have this tremendous ability to take off. So this is a slow motion recording, and it shows us, first of all, that they use lots of joints, and so this is why the effective mechanical advantage makes sense. Which we touched on last time, and I'll repeat that. And by the way, those of us who do biomechanics, or a lot of us, are interested in rapid behaviors, and so we make these kinds of recordings using a high-speed video camera. So normally, when you film with your phone or some other camera, you're shooting at 30 frames a second. That's the standard frame rate. If you want to be cinematic about it, then it's 24 frames per second. It gives you that cinematic quality. Whereas high-speed video cameras record more at 1,000 frames per second. So when you play it back at regular speed, you have many more frames per second to play, and so it slows it down, and you can really capture rapid behaviors quite well. Okay, so the locust leg has lots of joints in between, as does the frog, and so when the frog takes off, it just looks like this accordion that unfolds, and it allows them to accelerate and take off. So actually, we've kind of already covered a lot of this. So I mentioned that there are lots of different levers. So what I mean by that is this slide here, where we went through that the relative placement of the load in the muscle and the joint, the same principles can apply with any one of those arrangements. And then we talked about the effective mechanical advantage, okay, and this is where we left off. So an observation made way in the first week about smaller animals being more crouched has an implication on their effective mechanical advantage. So if the out lever of your lever system spans multiple joints, and just to remind us of how that works or looks. So here we can see, so what we're doing is we're skipping over all of these joints in between, and we're just focused on the one joint where you've got the muscle on one side of that joint, and then all the other stuff on the other side. And what we can do is just take the distance between that joint and this axis where the force is generated, and that is our out lever in this situation. So the effective mechanical advantage, it's basically just the mechanical advantage. It's the output force divided by the input force, but the way that you can calculate it is really simple. You basically skip over all the joints in between, and as long as you know where the force is pointed, then you can measure this distance r. Okay, so let's, now that we've reminded ourselves of the effective mechanical advantage, we can see here what's highlighted in green are the out levers of 3 joints. So this red arrow is the force that's pushed against the ground. So if the animal were still, that would be equal and opposite to the weight of the animal. This is known as the ground reaction force. So as you're sitting in your chair, you have a chair reaction force that is countering your weight. And in the context of doing an experiment on terrestrial animals, people measure the ground reaction force with something called a force plate. It's just a plate of metal with strain gauges attached to it that allow you to record a voltage that is proportional to force. And so you can do that in 2 dimensions to get the real angle of the ground reaction force, shown in red. And then you can calculate the out lever for the effective mechanical advantage of every one of the joints. And you can see that on the right, with the more erect posture, which is more typical of like an elephant or a horse, that you have smaller out levers. And so the effective mechanical advantage shown right here is the in lever divided by the out lever, just like the regular mechanical advantage. And so if you make those big R's small numbers, then you get a larger effective mechanical advantage than what you have for a crouched posture. Okay, so small mammals have the upside, again, because there's this trade-off between mechanical advantage and displacement advantage, you get more displacement advantage. And so vertebrates that tend to be smaller, have more crouched postures, have a greater range of motion. So we have this video on the right of the elephant, and then we can contrast that to like a dog, which is not, it's sort of an intermediate size mammal, but they have greater range of motion. Okay, so we can use the effective mechanical advantage to talk about these principles of force output and mechanical advantage and apply them to multi-jointed systems. So that was the rendering of the locus that I thought we were on, so here we see it again. And the locus leg has been kind of like a classic, well, there's not a huge literature on it, but it is sort of a classic system for consideration of elastic energy storage. So this is something that Dr. Azizi presented in his lectures, that the tendons that are attached to muscles are elastic. That means that they can store energy and then release it like a rubber band. And so sometimes those elastic mechanisms are just quite simply having a muscle attached to one tendon, and that tendon stretches and then it releases. So a human example is that when we run, you hit the ground, you stretch your Achilles tendon, and that helps to propel you forward on the next stride. And so we're constantly storing and releasing elastic energy as we run, and it greatly enhances our fuel economy as we run. If we didn't have that mechanism of elastic energy storage, it would be much more energetically expensive for us to run. So the locus story relates to this issue of mechanical advantage. So just as a reminder, this is an image from Dr. Azizi's slides where we have this extensor muscle. And what it's going to do is it's going to kick out this tibia here in a clockwise direction. And it includes this semi-lunar process, which is the source of storing the elastic energy. So the way this can be shown schematically, I know the geometry here is a bit unlike what's up here, but functionally, this is the way that it's thought to work. That essentially, that semi-lunar process, which provides elastic energy storage, it also compresses. And that matters as you've got the extensor muscle pulling on this tendon up here. In fact, insects and other arthropods actually do not store elastic energy in their tendons, the things that attach to the muscles, but instead they need other structures. So here, this is what the semilunar process provides. The reason being that those, their tendons are very stiff. It's called an apodeme. And so vertebrates have this ability to just store elastic energy in our tendons. That's great. They're directly attached to muscles. Invertebrates, such as the locust, do not have that. But the semilunar process is actually even more resilient than tendons are. So anyway, as the muscle pulls and it stretches the apodeme somewhat and stores some elastic energy, it's really compressing the semilunar process. But what I want you to notice here is what's on the left. That is the moment arm, okay? So we just talked about how the posture of mammals affects the out lever length, right? And if you have a big out lever, your mechanical advantage is going to be smaller. If you have a big in lever, that's like the long handle on the crowbar, then you're going to have a greater mechanical advantage and an ability to generate more force. So what this length of this black bar is showing us is the distance between the joint and the direction of force generated by the muscle. Okay, so that is the in lever length for this mechanical system. And initially, as the muscle generates force and compresses that semilunar process and stores elastic energy, we have a situation where that in lever, yes, is relatively small. Okay, so if my in lever is small, my mechanical advantage is not good, then that's like having a crowbar with a tiny little handle to it. Okay, you're going to get a lot of resistance when you try to pull a nail out of the wall because you've got a really bad mechanical advantage. And so as you're generating force, it's not going to move, so the nail analogy would be like you're pulling on it and you're not really generating any motion. And that's exactly what happens at the beginning of this process. So these muscles are generating force. They're pulling on this apodeme. They're compressing the semilunar process. And that's in large part because they've got this pathetic little in lever length. Okay, they're dealing with a puny little pathetic crowbar. And so initially, when the muscle's first activated, you've got this tiny little in lever, tiny mechanical advantage, and a lot of resistance to the force being generated by that muscle. If there wasn't resistance, you wouldn't be able to compress the semilunar process. You wouldn't be able to stretch the apodeme, right? You need that resistance. Otherwise, the system would just move, and the force would directly translate to the tibia rotating. Because there's resistance, then you get a stretching of all of these those elastic structures. Okay, when it finally starts moving, because you are generating some force, the moment arm changes. And in particular, it gets longer. So just again, this vertical bar is just showing us the distance between the joint and this axis of force generation. And you can see, yes, that's a bigger bar than that bar. So what happens is that, and also the semilunar process is now recoiling and returning some of that elastic energy, and so it's actually moving the joint, and that does help generate power for the system. But what we want, the take home here is what's happening with the geometry. So since the in lever is getting bigger, effectively for the crowbar analogy, that would be like the crowbar just is growing longer. So as we generate force, we're getting a lot more force output on our nail on the wall. And we see that down here. So we've got a bigger in lever, we've got a bigger mechanical advantage. All right, so what you have is this one joint system storing elastic energy, and by virtue of a change in mechanical advantage as it moves, we have this benefit, okay? If we didn't have this change in mechanical advantage, like I said, there wouldn't be the opportunity to store elastic energy, because the muscle would contract, you'd have very little resistance, and the tibia would just rotate. Instead, there's a lot of resistance because the leverage is so pathetic and bad that you really need to pull with the muscle on these elastic structures. That's compressing them. And then when the system starts to go, we get a release of more power than we otherwise would. So it's providing an example of variable gearing. We've been thus far just thinking of joints and the geometry as this static phenomenon, but we can see examples of it changing, and sometimes those changes have a real upside functionally, because in this case, we otherwise wouldn't be able to store that energy elastically. Does that make sense? Any questions about that? Okay, so we're going to take this idea and apply it to the frog example. And so Miles is very happy because we're talking about his favorite organism to study. And so here we again have that video of the frog, and we can see this sort of spectacular unfurling of the legs, and that's because they're so good at jumping. And there are some points that I want to make about jumping itself here that relate to elastic energy storage and mechanical advantage. So first of all, as a jumper, you're going to be able to propel yourself further if you can exert more work upon the ground. So I mentioned the ground reaction force. If you can apply more of that force for a longer period of time upon the ground and have the ground deflect just slightly in response to that, then you're essentially exerting more energy on the ground, and that will translate to more energy that propels you forward. So you can essentially think of the amount of work done on the ground as being beneficial for the kinetic energy that you leave the ground with. Okay, so more work, good, if you're a jumping organism. And there's different ways of thinking about work. And what I want to focus on is the first derivative with respect to time. What's the first derivative of a work with respect to time? What's the rate of work? What do we call that? Anybody? Work. Another term related to work. Power. Thank you. Yeah. So since power is the first derivative of work with respect to time, then if you integrate power, like let's just say you measure how much power you're exerting on the ground, and you integrate that over time, then you can calculate how much work is being generated. So quite often, if you're interested in measurements on a moment-to-moment basis, that measurement is what you want to focus on. If you're interested in its integral, basically you add up all the powers to get the work, and that's just what this is. We're just saying from one moment of time to another moment of time, if we just add up all of the power values and you multiply it by the increment in time, that gives you the work. All right, so what the reason why I make that point is that it justifies, so if we accept, okay, we want to generate as much work as possible on the substrate, then we can do that by maximizing the power, basically the rate of work that we're exerting on the ground. So the bottom line here is that jumps go further if power can be maximized during the jump. So this is really the goal of a jumping organism, is that I've got a certain amount of work that my muscles can generate as I contract them. They'll move some distance, they'll generate force. But really, power is the quantity that matters in this context. And this is sort of an example in biomechanics. This happens a lot where it's like, well, is it displacement that matters? Is it force that matters? In this case, it's power that matters because it affects work, which affects the ability to generate kinetic energy. So in different contexts, you have different properties, mechanical properties, energetic properties, that matter sort of in the biological sense. Okay, so let's look at power. And this is a study. So Rich Marsh is now an emeritus professor, but for years and years he was a muscle physiologist who worked on frog jumping. And what we have here is a very interesting graph. And this is pretty typical of people who are wondering, like, there's some feat being achieved here by my organism. How, is this, can we explain this just strictly from the power that comes from muscles? Or is there some other way that they're gaining power? And so what you can do is you can record the motion of a frog jump, and you weigh the frog, and you can estimate, for example, just take the kinetic energy once it leaves the ground. You can estimate how much energy must have been imparted for that to happen. And then you can take the amount of time that they were in contact with the ground and infer how much power must have been generated on average to achieve that. And so what we see with this line here is just that calculation. It's the average takeoff power for lots of jumps. In this case, they were varying temperature, and that's because muscles are temperature dependent. They tend to do really well with temperature until they don't. So eventually, if you overheat a muscle, then it will fall off a cliff. But you do get this increase in power output as you crank up the temperature. Okay, so in this case, we're not so much interested in the temperature. It's just allowing us to tweak the system and see how it behaves. Now, down here is what's called isotonic power. So instead of doing that estimate of power based on your sort of black boxing the musculoskeletal system, you're just taking a measurement basically of speed and then and mass, and you're inferring the takeoff power. But what you can do is you can then extract the muscles that are responsible for doing this, the leg muscles, the ones that are activated in particular to power the jump. And if you actually directly measure power, then that's what's down here. So we have a bunch of circles here. That's one for each experiment. The mean values are shown as that dash. And so we have a bunch of frog legs at different temperatures. And you can see that, yeah, power goes up. But what's startling here is, like, it does not explain their ability to take off. This is a Cuban tree frog, by the way. Cute little frog. All right, so let's see, I've got some stats here, so the tables are less fun to look at, but what you can see is that the isotonic power of 240, all right, we got watts per kilogram. That's because power does scale with mass, and the different frogs come in different masses, so we're interested in that power density, how much watts per kilogram of muscle can be generated. And so we've got this value of 240. Well, that's like 1/3 of what's required to actually take off. So how is it possible that they're actually taking off is the question. Okay, that's what this study is concerned with. So what's the answer? I've already told you what the answer is. What's the answer? Just return it back to me. Sorry? Yes, stored energy. Thank you. Yes. Elastic energy storage is the answer. Okay, so if you've got this situation where you know that the power output far exceeds what a muscle can generate, there must be some way that the organism is taking muscle power and storing it so that it can then be released to enhance the power being generated by the muscle. So you can think of elastic energy storage as like putting power on layaway until you need it. And then in addition to the power being generated while the jump is happening in this case, you're also getting the stored elastic energy to augment that. And it's not like this subtle effect. We're talking about a 3-fold difference here between what the muscle can do directly and what's being delivered. So 2/3 of the power is being delivered by stored elastic energy here. Now, in order to understand, so spanning multiple studies about this, people really interested in frogs, they came to be able to explain exactly how the energy is stored in the tendons. And so that's what I want to tell you about. So there's this really cool technique. It's called, the acronym is XROM, is like X-ray something, something, something. I don't remember the rest of it. Anyway, it's basically taking X-ray movies with, again, high-speed video. But what you also do is CT scans of the skeletal system. And then you place that virtual skeleton in a 3D context. So you're taking your X-ray movies are taken from at least two perspectives, so you have it in 3D. And then you place the bones in those 3 dimensions in the animated X-ray movie of the animal. So they give you very specific information about how the bones of a frog, in this case, or any animal, are moving with respect to each other. It's a really cool technique. Super time consuming, a lot of work, but people are doing it all the time these days. So here we see the cranium, the head of the frog, and here are the leg muscles. And what they've superimposed in 3D here is the ground reaction force. I don't know why they oriented this horizontally. This would be a frog that's actually taking off. And what I want you to notice, so I'm going to play this, and what I want you to notice is what happens with this vector. And we can see already, so the frog's not going to be moving initially, and we can see that there is a ground reaction force. So that could just be its own weight. But we'll see this grow before the animal actually moves. So you can see I'm playing it. So you can see that the arrow takes off and then the animal actually starts to move. And that's partially reflecting the mechanism for elastic energy storage, that the muscles are generating force before the animal really starts to go anywhere. And so here we see a time series of that recording. So we can see that that as the animal does actually take off, you see this growth in the ground reaction force. And so the way that this looks as a function of time is something like this. So here we have time on the x-axis. Up here is force. So the dashed line is the ground reaction force. So that is the red arrow that we see there. And yeah, it goes up. The ankle extension, so that would be this. So this is a frog, and the black dots are joints, and this is muscle. What muscle is it, Miles? This is a gastroc. Okay, this is a gastroc muscle that's generating a torque around that particular joint. But there's other muscles that are contributing. This is the main focus. And so that ankle joint right there is shown in purple here. And so here you can see the ground reaction force going up and up and up at a fast rate, whereas the ankle is barely moving until it really goes. And it starts to go when that force peaks. And what we see down here are two interesting properties. So first of all is the power at the ankle. So primarily generated by that gastroc muscle. And so not surprisingly, we see it go up with the force. But this graph here is the moment arm. And in particular, this is the out lever. So we talked about how the in lever changes dramatically in the locust. In the case of the frog, the mechanical advantage changes as well, but it's through the out lever length changing. And so, and in particular, we can see that it's initially a big out lever, and then we have a drop in the out lever. So recall that mechanical advantage is the ratio of the in lever to the out lever. So our crowbar, we want to have a high mechanical advantage. We want the crowbar handle to be long, and we want the output, the out lever, to be really small. In this case, it's the opposite, that the crowbar is almost reversed. You have a big out lever initially, and then it gets smaller. That black line in the panel B goes down as they take off. And so as a consequence, it's almost like exactly the opposite of the locust. So instead, in the case of the locust, we saw the in lever get bigger. In this case, the out lever is getting smaller. And as a consequence, we have the same thing happening. That is, the effective mechanical advantage starts very low, and then it grows as they take off. And this is beneficial for the same reason as the locust. So instead of that little semilunar process, that little pad that gets compressed, because this is a vertebrate and vertebrates have tendons that are highly elastic, as the gastroc generates tension, it's going to stretch the tendon, which is not only right here on the end of the muscle, but it also wraps around that joint and serves as a long piece of collagenous tissue that stores elastic energy. And so while that ankle is staying pretty fixed and we have this elevation in force, that tendon is just getting stretched and storing power so that when the animal actually starts to move, we've got both the power generated by the muscle itself in addition to all of that stored elastic energy from before it started moving. Now, because you've got poor leverage initially, the resistance of the mass of the animal is, and its poor leverage are going to facilitate the opportunity to have the tendon be stretched and to store the elastic energy. And so for that reason, this mechanism is known as an inertial latch. That is, the mass of the body itself is providing resistance. Because the muscle has such crappy leverage, then it just generates tension and just pulls on all those tendons. Nothing happens until something finally happens, until the body actually starts to move. Just to use an analogy on stored elastic energy, like a bow and arrow is an example of elastic energy storage. So you pull on the string and the bow deflects. The storage is primarily in the bow, a little bit in the string, and then you release it. And one thing about elastic mechanisms in biology is the details of how the energy is released. You need some sort of a catch in order that you're straining elastic tissues to provide the opportunity to release those tissues. And so in the case of the locust, we saw that the effective mechanical advantage played a role, and that poor leverage allowed for the elastic energy storage. Here, it's very similar. You've got poor leverage initially, and then you combine that with the weight of the body in order to store the energy in the tendons, which then gets released. Any questions on this? Yes?
For the grasshopper, is that also an inertial latch? Or I think I've heard.
Well, yeah, so in that case, if, yes, I think, so the term inertial latch, I think, has only been applied to frogs. But in actuality, the resistance is from the mass of the body, and therefore, in principle, it's the same idea. And so I would use the same term for that situation. Any other questions? Okay, so we're going to do a little problem together. And so this is similar to the last meeting we did, a problem that revolved around displacement advantage. So this one revolves around mechanical advantage. So we've got a mouse, gastrocnemius muscle, has an in-lever length of a particular value, 5 millimeters. And we have an out-lever length. So we want to know how much muscle force can it exert on the ground. So we want the force output if we have an input force of 10 millinewtons. Can you still read it? Still visible again.
That is simply the outboard or the because if it generates a force then that means what is exerting on the floor is what is the force that's out. I'm working over here. That's how you guys take that. No, you guys love me.
Oh, they're different. I didn't realize it.
Who needs more time? Okay, since most of you are done, I'm gonna move on. Okay, so again, I might have messed up the calculation. This is the first time I've done this particular calculation. Okay, so it's always helpful to draw a free body diagram. Okay, so here we have the gastroc muscle, and again, we've got this situation potentially with multiple joints, and we're given the out lever length, which we just take as that distance as it's drawn there. Okay, so did I get the numbers right? Okay, so the in force, 10 millinewtons, okay, correct. The in lever length of 5 millimeters, and then we've got the out lever length, I wrote it wrong, oh no, I did it right. Okay, so 30 millimeters is indeed 3 centimeters. I did that so that I'd have the same units. And I set this up as a balance of torques, but you could just jump to this step here, you know, if you happen to remember that the mechanical advantage is the ratio of the in lever to the out lever, then you could take that by itself and you could plug in the numbers to get that mechanical advantage. And then if you take the input force and apply that, then I ended up with this number down here. Did everybody else get the same number? Yeah, okay, good, all right, I did it right.
What, is there like
Yeah.
a preferable units that you need to use? Like, cause what if instead of going to millinewtons, you went to like centimeter newtons?
Centimeter newtons is not a thing.
I mean, sorry, I mean, yeah.
Like centinewtons or
yeah,
or
that's right.
micronewtons
Yeah,
or something
yeah.
like that. No, as long as you're using SI units, you're good. You know, there's fewer digits to worry about when you use something like millinewtons, and also if you're just given convenient units to begin with, then you don't have to bother with converting it. So, but no, the correct answer is the correct answer. So if we did this as 1.67 times 10 to the minus 3 newtons, that would be just as correct an answer as this one. Yeah. There any, yeah, go ahead.
Is this at all comparable to conservation of energy?
Is this comparable to conservation of energy in the way that it's set up? Well, yeah, so yes, in the sense that it's a conservation rule, and so you have an equivalency in both cases. So yes. So another thing that I'll just this is a teaser is that if you're assuming that your lever system conserves energy, then the amount of energy you get out of the system, the output end of things, is equal to the input end of things. So you can set up a lever system problem as a conservation of energy problem. Here we focused on torques and forces, but you can also start from the premise that the work that I'm putting in, so that's the product of the force and the amount of shortening, that work is equal to the work out. In this case, it's a static situation, so there's no work in, so you wouldn't need to do that. But you could conceive of a problem where if you had the amount of force and the amount of shortening, then you could calculate how much work was being put into the system, and then if you need a ground reaction force, you could figure out the work out of the system. So I was sort of skirting around that, but that's good you brought it up because yes, it can certainly be set up that way. Yeah. Any other questions about the calculation? No? Okay. Yeah, it's very similar to the displacement one, but it's a focus on force. Okay, so we've seen two examples, both the locust and the frog legs, where variable gearing turned out to be super important for the ability to store elastic energy, which then powers a jump that far exceeds the capacity of what the muscle will be capable of itself. So with the very limited time that's left, I just want to start on the next topic. Okay, so skeletons 2, the return of the skeleton. So here we have our schematic for the rigid skeleton. But in the first week, I alluded to the fact that not all skeletons are rigid. Your tongue is an example. For those who have a penis is another example of a structure that can change its material properties just by virtue of the dynamics that I'm going to talk about. Basically, there's an inflation of blood, which makes a penis larger and stiffer. And so between that and the tongue, and then also our internal organs also have a variety of forces that are transmitted through our blood vessels and our viscera, which also serve as these kinds of soft skeletal systems. But if you look across animals, and in particular you look at invertebrates, you see these like spectacular examples of hydrostatic skeletons. So here's like a beer bottle. This might be a really sad video, but it's like an amazing feat of escape by this octopus here. And octopus are actually really fantastic in their ability to change their coloration pattern. They can really blend in. Anyway, they can contort into really small spaces and do these sort of wonderful feats. And of course, if they had lots of hard parts, they wouldn't be capable of that sort of thing. We have, like, for example, earthworms that can burrow quite well in soil. So muscular forces are being generated just like in our own bodies. and those forces are transmitted through the body to change the shape of the body as well as exerting forces on the soil. So it's a skeleton just like a rigid skeleton, it's just as valid, and so it deserves some of our attention. And here we see examples of lots of other, so here again we see an octopus. Its arms are all muscle, and those muscles are organized in a way that allows them to contort and adopt a variety of shapes. Here we have a sea anemone. Sea anemones, you can see them in the intertidal. When you go to the beach around here, they have two cell layers. They have an inside layer and an outside layer. There's not much to them, and they have a mouth that's in the middle of all these tentacles here. And on the inside, in the lining of a sea anemone, are cilia that serve as a very low-grade pump that can allow the body to inflate. So when you go tide pooling and you see the deflated, sort of pathetic-looking anemone, that becomes very different when the tide rolls in and they start to activate those cilia, pump up the body, and then you have an inflation of the whole body when that happens, including, the space inside the gut is continuous with these tentacles as well. And here's just a cutaway of a blood vessel, just showing us that blood vessels are inflating and dealing with the pressures of the blood pressure and expanding under those pressures as well. So some of the dynamics that make sense for like a sea anemone apply to our own blood vessels as well. And many engineers are interested in sort of capitalizing on our understanding for soft skeletons, how they operate. Here we have an example of a little robot that was generated. Apparently not quite a robot, but it's inspired by a stingray or a skate, which with this undulatory swimming pattern. But these are very small little devices that they've infused with cardiac muscles, and they are capable of activating those cardiac muscles by exposure to light. And the whole system operates as a soft skeleton. So there's a rigid central region shown in yellow there, but the ability of the sort of wings, so to speak, to flap, and that's one right there, and so it's swimming along as it gets exposed to the light that's shown here. So anyway, it's just to show you a little taste of some of the wacky things that engineers can dream up with this application of soft skeletons. Actually, soft robotics, being able to build robotic devices that have some of the features of soft skeletons, is a really big area in robotics right now. So for example, microsurgery, people are using soft robots and those kinds of applications. So it's actually a really kind of growing area in the engineering world. So I'll mostly be talking about this on Friday, but just to give you a bit of an introduction, there are a variety of soft skeletons. So the tentacles of an octopus arm and our own tongue is an example of what we call a muscular hydrostat. That's essentially a whole bunch of muscle tissue just packed together in different layers. And those little packages, of cells are all fixed in their volume, they're filled with fluid, and they all exert forces on one another, and they can move by virtue of those mechanical interactions. Elephant trunk is another example. We have what's just called a hydrostatic skeleton. So this would be like the earthworm example. So earthworms are arranged in segments. Each segment is almost like a water balloon itself. And it's wrapped again in muscles, and if you squeeze a water balloon, it'll sort of pop out in another direction, and so that basic principle applies to how earthworms generate locomotion. And then there's the example of the hydraulic skeleton. So I mentioned a human penis. It turns out that mammals in general have a similar structure, and that operates by inflation. And so a hydraulic skeleton is unlike the other two in the sense that the volume of fluid that inflates the structure is not fixed. So a tongue or an elephant trunk has all these cells that are essentially fixed volumes of fluid, and the muscle fibers then act on that fixed volume. Same thing for the hydrostatic skeleton. Whereas a hydraulic skeleton is more what we see in the sea anemone. it changes its volume because it inflates. And same thing for like a jellyfish, for example. So all of these systems operate by principles that you could apply to water balloons as you sort of squish them and watch them behave as they deform in different directions. And so that's what I'll pick up on Friday.